record. Is it recording? Good. Okay. Hi. I'll talk to you about something I've been thinking about in the past 2 or 3 years in between writing ARC grant and panicking about life in general. I assume we all know that earth elements are important because we make magnets and wind power and electric cars, and we find them in carbonatites. So I will not show the mandatory slide of, right? I'll just skip that and go straight to the thing. Okay, so starting with fluids. Usually when we think of fluids or liquids in the earth, we usually think of either magmas. So here's a picture of a basalt dike. Or we think of hydrothermal fluids, so H2O, with some stuff in it that can alter or deposit new minerals in hydrothermal veins, okay? So this is silicate, and this is the remnants of reaction with H2O, and this picture is from the Rhodos ophiolite in Cyprus, which is a beautiful, beautiful place. Now, you can combine the two and have a magmatic hydrothermal system. So here's an example of a porphyry copper deposit, one of the best known magmatic hydrothermal system. And the idea is that you have a magma chamber, and as it cools down and decompresses, you saturate bubbles of water, H2O, or elements, copper, zinc, moly, gold, whatever, partition into the bubbles. Then the bubbles go up, go somewhere, and they get outside of the action magma chamber, and they do some alteration and deposit in all deposits, in this case, a porphyry copper deposit. And indeed, when you look at some of those, so here's an example of a picture from Cadia, where we have a rock of some sort, and in that you have veins or cracks where fluids that came off a magma made this, which is a vein of quartz and bornite and chalcopyrite. So fluids extracted ore elements from the magma, then the magma stopped being important, and the fluids went somewhere else and made a deposit somewhere else. This is important because when we're exploring for things, we want to know where the mineralization is. Is it in the magma? Is it at the top of the magma chamber? Is it in all kinds of different structures? Now, in carbonatites, you often see similar things. So here's an example from Stockbridge. Am I saying it right? Stockbridge, okay. And thanks to Christina, where we have something that looks kind of similar. You have rock, some sort, and in there you have a vein that has ankerite, which is the iron-rich version of dolomite, and you have some rare element mineralization. So carbonatites, the mineralization in carbonatites is sometimes interpreted as a similar magmatic hydrothermal system, okay? When you actually look at the minerals themselves, they often look hydrothermal. So when you look at this stuff, okay, I think everyone here will agree that this is not crystallization from magma. This is crystallization from a fluid, okay? And this is even more obvious when you compare that to actual magmatic deposits. So here are examples of carbonatites with eudialyte, which is a magmatic crystallization of earth elements. And when you look at that, it's obviously an igneous plutonic rock with phenocryst, and you can see all kinds of crystal structures and shapes and stuff. So obviously this is magma. What I showed you before was not magma. Okay, so this is an idea that's very common in the literature, and this is quoting from the abstract of 3 papers on mineralization in carbonatites published in the past 2 or 3 years. So in here we have mineralization, and then you have pulses of carbonatite-related rare element rich fluids. So you have the carbonatite, then you have other fluids that made the mineralization, and you deposit the elements because you have some meteoric water. Or in other case, you have hydrothermal upgrading of an earlier phase, and it's important for mineralization in carbonatite. So you had some kind of mineralization, then later fluids made the mineralization better, more concentrated or more something, okay? Or another example where you have ore fluids, sulfate-rich, acidic, chloride complexes, transporting earth elements. Is it? I don't know. So, well, let's just have a look. So I would like to look at this word here, acidic. It's a carbonatite. Nothing is acidic in carbonatites. there's an idea out there that you have the carbonatite, it dissolves acidic fluids, then the acidic fluids back react with the carbonatite and make some mineralization. My question is, if it's all full of calcite, how do you have acidic fluids in the first place? Okay.
Michael, do you think the person or persons who wrote that were thinking about the old-fashioned words that were used in English rock generally, from basic to acidic?
No, they were specifically talking about low pH. Okay, so and there are a lot of issues here, which I think all of this is just wrong. Okay, and let's see why. First of all, experiments show that when you look at the fluid to melt partition for rare earth elements, you have 0.0 something. So if you have a fluid and that fluid has halogens or whatever, all elements, rare earth elements, stay in the melt. They don't like going into the fluid. Interesting. And this is something that I also see. So here are some of my very old experiments back in the day when Hugh O'Neill told me it's a good idea to test something. So I did, and I never did anything with that. But the idea is that you have, here's some apatite. This is all quenched carbonatite magma. And all of the white stuff are rare earth element rich phases, apatite mostly. And in here we have bubbles of some fluid, H2O and CO2. And you can see that the rare earth elements are in the melt. They're not in the fluid. Okay. Here's a beautiful secondary electron image of one of those bubbles. And you can see that the surface of the bubble, like the walls, there are no rare earth element rich phases. It's just the same thing as you have in the melt itself. Other than that, here's a wonderful paper by a good friend, Tibor Guzmix, and he looked at natural rocks and saw liquid immiscibility. And in there you have a silicate melt, a carbonatite melt, and a vapor. Okay, and that vapor sometimes has some kind of condensate in it. When you look at what the condensate is, it's just sodium carbonate and sodium bicarbonate. There are no ore elements, no rare earth elements, nothing heavier than sodium and a bit of potassium. You may also have a bit of halite, sodium chloride, but that's pretty much it. There is fluid, it doesn't take anything in it. Okay, and all of those papers that claim that you have fluids that can transport stuff, they very often they cite the series of papers by Miglisov and Willie Jones, where they say that you can transport the rare earth elements with chloride and sulfate. Yet we know that if you take lanthanum chloride and put it in a bucket of water, it dissolves. Same thing with sulfate. But what is often missed is that fluoride, carbonate, and phosphate deposit rare earth elements. And it's just the second part of the same sentence. Okay. Now, guess what we have in carbonatites? Obviously, carbonate, also lots of fluoride, and phosphate is very, very common. Now, solubility is often determined by the least soluble thing. Okay. If we take sodium chloride, very soluble. If we take sodium aluminosilicate, albite, not so soluble. So the fact that you have fluoride and carbonate and phosphate in a carbonatite system means that you probably will not dissolve earth elements in a fluid in the first place, even if you have chloride and sulfate. Another thing that is often missed in fluid inclusion studies in carbonatites is that the alleged ore-forming fluids miss a very important thing, which is the ore. When you look at porphyry copper deposits, here's an example from El Teniente, chalcopyrite. Okay, so I think there's no question that this is an ore-forming fluid because you have a fluid that has copper in it. Okay, and then when you move the fluid and then you change whatever temperature, boiling, pH, you can deposit that and make a wonderful ore deposit. When you look at carbonatites and look at fluid inclusions, you don't really see any ore. So I mean, sometimes you have a solid. Those solids are almost always the same thing as we saw in the condensate, sodium, carbonate, or sulfate, or stuff like that. Interesting. In that same place, they also have melt inclusions that have heaps of stuff in them, yet they say high rare earth elements in the exhaust ore forming fluids, which kind of makes me think that they had a preconceived idea, and regardless of what the evidence is, like, okay, yeah, fine.
So what is data?
Here,
Yeah.
solid, salt. I don't remember. The S?
Is salt or solid?
Yeah.
Silicate.
No, it's not a silicate.
D
Bubble.
bubble. Okay.
I mean, it looks like a bubble. I don't remember, but yeah.
N.
I don't
Sorry.
know.
It's
I can check later.
question.
Naturally.
Oh, no, yeah, that's good. Yeah.
Okay. And this goes to show a point that a fluid that you find in the ore is not necessarily the ore forming fluid. And I think this is Mr. Raman. And this is an important point for all ore deposit studies, not only carbonatites, because an ore forming fluid is the one that dissolves the ore. When you're looking at the ore, it's already deposited. So something to think about. Okay, here's an example from a fluid inclusion in bastnasite, which is ore, and it's some kind of sulfate. Okay, does that mean that sulfate was important to make the bastnasite? I say no, and I'll show you later why that is the case. Okay. Fluids and carbonatites are very complex. So here's a wonderful review of fluid types you find in carbonatites. You have type 1, type 2, type 3, type 4. There are some of them are dense, some of them are not as dense. You can have all kinds of processes leading to all of them. Something that I wanted to do was try to make some sense into that experimentally. Okay, so those are observations from nature, and I think the best way to understand the rock is to make it yourself. So let's go and do that. Okay, and to do that, you just zoom out of carbonatites of the inclusion and look at carbonatites in deposit scale. Okay, and many of them have a predictable geometrical structure. They're circular, okay, and then you have, as you go from the outside in, you have in here an example in Russia where you have calcite. As you go in, you have dolomite, and then you have ankerite. Here's another example from Canada where you have calcite on the outside. As you go in, you have dolomite, and then you have a ferrocarbonatite, which is kind of ankerite, just the iron-rich thing. Here's an example from Fen in Norway, where phenites come from, and it's not as clear, but you still have a sequence of calcite to dolomite to iron. Okay. Usually the mineralized parts are in the iron-rich parts of the carbonatites. Why is this happening? So in a sense, you can think of this as a magma chamber. Whether those are actual magma chambers, it's a very good question. I think they're not, but just for the discussion now, let's think that they are magma chambers. So what happens when you fractionate a carbonatite? So we know from silicate system that when you fractionate, you first have olivine, then pyroxene, then plage, all of that. What happens in a carbonatite? So there's this paper, it came out in 2017. I think one of the most important papers ever published on carbonatites, and I think it should be cited so much more than it is, because it is something very important. What they did, they tried to explain Odonolenga, which is this volcano in Tanzania, where they have lavas of natural carbonatite, and the question is, how do you get them? What they did was just take melt inclusions, composition of melt inclusions that are found in high temperature carbonatites, and try and make a phase diagram out of that based on a natural-like composition. So they did a bunch of experiments, and they showed that they essentially do a phase diagram. What it tells you that you can fractionate a carbonatite if you start here and you crystallize in calcite and even more calcite and calcite all the way down. Even if you have less than 58% of calcium carbonate in the melt, you're still making calcite, which I think is pretty amazing. At some point, you stop making calcite and you start making sodium and potassium carbonates at a very low temperature. So we will talk about below 600 here. And it's also kind of similar to what they had to the composition of the natural one. So this is one way to function the carbonatite. My issue with that is that it didn't have any magnesium, it didn't have any iron, no earth element. So I said, well, let's be inspired by this, make something that looks like we have in other carbonatites in nature, and do that. Now, because of laziness, I didn't want to run 20 individual experiments. So I used back then we had the wonderful new automatic piston cylinders. So I said, well, what if I just go and take one composition and cool it down slowly from high temperature to low temperature? So I made two compositions. I made more, but I'll talk about two now. And here's me just playing with lava. Has nothing to do with the experiment, just like the picture. So I made a composition with calcium, magnesium, iron, phosphate, sodium, or potassium, rare earth elements. Obviously, it's a carbonatite, heaps of CO2, water, fluorine, chlorine, a bit of bromine, because it's an experimental trick to make things bigger and prettier. And I put that in a capsule, take it to 1200 or something degrees, and cool it down slowly over 4 or 5 days. And this is something that many of you have seen several times. And I'll come back with this a few times in the presentation today. So what's happening? We're crystallizing things from the outside in, because there's a thermal gradient in the capsule. This entire thing is about a centimeter wide. This is up. Just rotate it so it fits on the screen. And we have a sequence of calcite to dolomite to ankerite, which isn't obvious here, but trust me, it's there. Calcite and dolomite from the other side, and heaps of apatite everywhere. So this is essentially a calcite, a carbonatite rock, where apatite is a very common mineral. Same thing with the dolomite. And then on the inside, I have this thing, okay? At the time, in that paper, which, so those experiments and the paper was written in 2019, I called this the hydrothermal cavity. Why? Because it looks like a hydrothermal cavity. When I opened the capsule, it went, so, you know, obviously wet. And it has those green things are potassium carbonates or bicarbonates, I don't remember. And the red stuff is some kind of quenchy amorphous thing that has potassium ion and rare earth elements in it, and a whole heap of other minerals. There's also monazite. So all of the purple things you can find. So here's one in here. So here's a monazite, another one over there. Yeah, so this looks very similar to what you find in nature. You have that sequence of calcite to dolomite to ankerite, then you have a mineralized part with iron and monazite or earth elements. I did another thing where instead of potassium or sodium, very similar thing where you have calcite and dolomite and ankerite, but those things are magnesite, which are zoned to siderite. Again, it's something that you see in carbonatites. The hydrothermal cavity looked to be different. Didn't have the same minerals, but conceptually it was the same thing. Heaps of sodium carbonate and berbenkite, which was the earth mineral in this case. The other thing that formed, which was very weird, is all of those things here. See, there's green and blue and pink and purple. So all kinds of weird minerals. Here are some pictures. I made a bonschtettite. I've never heard of that mineral until I made it. Here's a berbenkite. I made something that seemed like it was a berbenkite, just had way more sodium than expected, so I call it a natural berbenkite. Here's the siderite. It gets very bright here because it has rare earth elements in a solid solution. I didn't know that it was impossible, but there you go. And I formed all kinds of weird minerals, ruvelite and neighborite and all of those things, and many of them had a measurable amount of rare earth elements, okay? In total, maybe 1 or 2%. But the other thing is that all of those minerals are sodium something, sodium carbonate, sodium phosphate, so all kinds of combinations and mixtures where it's essentially a soluble mineral with some atoms of rare earth elements in them. Okay. So those things are soluble, right? They will not survive in nature for long. And we see that. So bermacite, again, a sodium carbonate with some atoms of other stuff in it, elements of barium, very common in carbonatites, except it's altered. You don't actually see the bermacite anymore. You see its alteration. And sometimes when they're nice, they're hexagonal. And then you can see the remnants. Here's another example. And sometimes they're not as pretty, but you can guess just from the mineral assemblage here. You have synthesite, barite, strontianite. So it's all of those elements minus the sodium.
Michael,
Yeah.
can I just take you back to the Max Schmidt and the thing?
Yeah.
What was the purpose of their paper?
Explain Aldeno-Langite.
To account for a range of compositions that are erupted as lavas at Aldonio-Langite?
No, so the problem was that up until then, the phase diagram that we thought existed was the one in gray. Okay.
With
So,
a thermal high between.
Yeah, so there's a thermal
Carbonate.
divide, and people didn't understand how you can just take this and fractionate it into an Aldonio-Langite type lava.
Right.
What they did, they added a bit of things. I think it was fluorine and some other minor components, and they showed that if you do that, you get rid of the thermal divide, and then you can just fractionate all the way down here.
So it's pretty potassium as well, wasn't it?
Yeah, they had a bit of potassium.
So it was really just to track from high to low temperatures what a carbonatite melt might do.
Yeah.
And you have taken that and you really are not talking about the miscibility between that kind of melt and a coexisting silicate melt. You're in your own little carbonatite world.
Yes. So the question of how you get carbonatites in the first place is a very good question, and there are heated debates on is it immiscibility or melting of the mantle or fractionation, all of those things.
It's not something you've decided to play with.
No. So I don't have a strong opinion on how to get into having a carbonatite.
How to get the top right-hand
Yeah.
composition, for example.
I accept that they exist.
Yeah.
Now what? Okay.
So now you're going to throw all kinds of extra elements in to see what happens between rare earth element bearing minerals and those that don't have rare earth elements in.
But why the spoilers?
Pardon me? Why spoil the story?
Yeah.
No, I just want you to know in case I don't live long enough to the end.
I'll take that as a compliment.
I mean, it's torrent of names, for example.
I don't remember them. Anyway, those things are soluble and they don't survive in the geological record. Yeah, so something about this hydrothermal appearance that we often see in ore deposits. It's there because we're removing the alkalis away. So you're forming alkali minerals with earth elements of all sorts. And I'm pretty sure that if I go and run 10 more experiments with slightly different compositions, I will make even more minerals. Okay. So I think it's not always easy to know exactly which mineral was in a carbonatite. I guess it's easy when it's a bermacite and it keeps that shape. Now, so we aren't actually moving rare earth elements around. Maybe on a small scale, on a hand sample scale, but if you want to mine the things on the excavator scale, they probably don't move that much. But what is happening is that we're redistributing rare earth elements from mineral A to mineral B. This could be important because when we're mining the things and we want to extract them, we know how to deal with bastnasite, we know how to deal with monazite, but there are all heaps of other minerals that we don't know how to do that. Okay? Yeah.
So you've got this reaction,
Yeah.
but you're sort of implying that it requires water to go from the left to the right. Is that right?
Yes.
It's not a balanced reaction.
It's not balanced, and it's not balanced at all because this is, for example, sulfate, and this is not a sulfate.
Yeah, I mean, this is what I was wondering. And so have you tried balancing it or you're using thermodynamic?
So no, I haven't. So other people did, and there are papers, on that, where it did a balanced reactions and it happens. The problem with doing a balanced reaction is that you have a lot of anions that can be phosphate, fluoride, that can move around on a local scale, and I'll show that in one of the later slides. So it's unconstrained. So I can write it in a balanced reaction, but is it grounded in truth? We don't know. So I'll talk about that in a few slides. I have an experiment running as we speak, where I'm trying to do that. It's in the lab just down the corridor. Okay, so at the time, again, this is from the 2020 paper. I came up with a model, okay, and all kinds of things here, but the important thing to say is that there's melt, and then there's a dotted line, which means I have no idea what's happening there, and then there's a fluid, okay? Two distinct things. There's a melt and there's a fluid, because I had the magmatic part of the capsule, and then I had the hydrothermal cavity. But when you look at things in nature, this doesn't look like it's crystallizing from a hydrothermal fluid. It looks like it's magmatic, right? I mean, you have the dolomite in between, which is consistent with what we know of the magmatic sequence. All the minerals, they look like phenocrysts, right? So,
cone layering at the bottom. It looks like you have cone layering at the bottom.
yeah, all this documentation. So it's like, it doesn't, like when you look at each of the minerals on the SEM, yes, it looks hydrothermal, you have all kinds of stuff, but overall, not so much. So how does that happen? And something that I looked at my experiments and I'm thinking, well, you know, if this is a hydrothermal cavity, and it was the solution from the magma that made this, so at some point there was bubbles, right? So at one point during that experiment, which I don't know because it went from high temperature to a low temperature, you'd expect to have magma with bubbles. And I didn't see any evidence for this actually happening here. Now, I do know that in other experiments where I didn't have the sodium or potassium, I did have bubbles. So here's one example where this had heaps of extra CO2. So obviously a bubble was here, and you can imagine that the bubble was floating up and the magma was still kind of below it and crystallizing. Or in this case, where I have all of those holes in here, now those look like cracks, they're actually not cracks. Trust me. And also at the top here, there was a bubble. And when you look at those things, there are no earth elements in those parts of the capsule almost, which is consistent with what we know, that earth elements don't partition into fluids. Okay, so then I started thinking and understanding that this is all a continuous thing, okay? There is no fluid exsolution at any stage, and if there is a fluid exsolution, it doesn't do anything important. Take some sodium out, but that's about it. Now, the problem was that with those experiments, it was actually very hard to show because it would have been ideal if at some point I would stop the experiment halfway through and check if there were bubbles. I never actually did that, but someone else did. Now, before I talk about that, just back to this. This is a chemically simple system, okay? No magnesium, no water, no iron, no barium, no strontium, no earth elements. What if we take this and just add more things to it? Phosphate and sulfate also. So this will keep on going down, right? Because this is how eutectic systems work. The more stuff you add in, the more fluxes, the more you can lower the temperature. So this kind of made me think, well, is this what is actually happening in my experiment? I'm crystallizing calcite, then in a magnesium-rich system, you will also have some dolomite here, and then just keep on going down and down and down, okay? Now, from the same Guzmik's paper, so what they did, they also included the fluid in there. So here's our melt, here's our fluid, and the fluid is just there, some sodium and potassium, CO2, H2O, and nothing else. It doesn't take any of the more interesting elements, which are here. Okay. So what we have is a complete and continuous differentiation sequence. So this is actually not a hydrothermal cavity. This is just the next stage of the rock. Okay. The question of is it actually?
But you call it a brine.
I'll get there. I'll get there. This one?
No. Okay.
This
I
one?
don't see pressure.
I think it was 1 kilobar or something close to that.
What are your experiments?
So my experiments were running at, they ended at 2 kilobars. They started a bit high. Okay. Now, a few months ago, this paper came out, which actually solved the problem that I had, where I didn't know if there were bubbles or not because I was only looking at the end result and not at the process. So what they did a bunch of how do you call them? Diamond enamel experiments, and they looked at that process. And the title is the transition from carbonatitic magmas to hydrothermal brines, continuous or exsolution. And their answer was, as soon as you have enough pressure, and enough pressure was like 1 kilobar, you have continuous thing. So that saved me from running a whole heaps of experiments to show that, which was very nice of them. Okay, now, okay, so we have this late stage.
I just have, if in a situation, we know it is like under high pressure and stuff, but if you have like those kind of alkaline carbonate fluids, and you get in a situation like one like that, where you go into like, you know, shower temp conditions, could you get a situation where you almost like mix like a alkaline melt from fluid?
So if you go to shallower pressures, you will have a fluid, but again, that fluid will probably not have much of significance, just like those condensates we had in some of the earlier slides. Yeah. And there is also at a lower pressure, there's something that happens there with retrograde solubility and all kinds of things. So there are complications, but for now, to make life simple, I'll focus on the higher pressure. Again, higher pressure being a kilobar, so it's not actually much. Okay. Yeah. So I was, you know, we have like a is it the melt? Is the hydrothermal brine? It's something weird. So you know, just looking through the literature, I found that wonderful paper on the carbonatite in Russia. Now, I usually don't like having walls of text on my slides, but I think this was is important, and let's quickly go through it. So you have melting fluid inclusions that you have a carbonatites formed from volatile rich alkali and chloride bearing carbonate melt. Okay, so a carbonatite essentially. Then first you have ankerite and calcite carbonatites at a temperature of high temperature. And then you have a second phase, something that happens later, where you have ferrocarbonatites, and this is from a sulfate carbonate chloride fluid phase at a slightly lower temperature. And they call it a brine-melt. And I think, oh, this is a wonderful name. This precisely explains the thing I have, because it's not quite a melt, not quite a brine, not a hydrothermal fluid. It's its own thing. So it's a brine-melt. So I adopted that name. And then they say that the brine-melt fluid, which is a word I like less, but the brine-melt had high concentrations of iron and earth elements, which is exactly what we see in those ore deposits. Also, they say that a subsequent hydrothermal overprint made the barite, fluoride, and earth elements. So again, we had the brine melt, we had a sodium or potassium rich thing that it dissolved, and then you had those things at the end together with the siderite. Okay. And if we take that into our phase diagram, so in here we have carbonatite melt and continuously evolves with no exsolution, or if there is exsolution, it doesn't do anything, it's just over there, we don't care about it, and then it becomes a brine melt at some point. Okay, so here's the old model where this was kind of unclear. Then we made a newer one, and this is from a paper in elements, and this beautiful diagram was made by Sam Brunfendley, not me. Where we just implement that. So we still have the calcite, dolomite to ankerite to mineralization, and sodium, rare earth, carbonates over there. So those are the Brine-melts and all those minerals. And at some point, it just becomes a BN, a binder, okay? Then later you have the alteration, and then you have what you actually see when you look at the carbonatite today. Also did that in a review paper the next year, where we have this figure, again, the same thing. We have a Brine-melt at the top here. And I thought it was a good idea to actually define what a Brine-melt is, because you could foresee a state where like no one actually knows where's the gap, like where does it stop being a carbonatite melt and where does it begin being a Brine-melt. So we came up with a definition, which is a H2O rich evolved carbonatite melt that lost the calcium carbonate, is now saturated with alkali or unrich carbonates, which I think is a reasonable definition. And in the same paper, we recommend that we stop using hydrothermal fluid when we're talking about carbonatite systems, because it is very ambiguous. Instead, that other fluid that we have there is something that we would like to call a synmagmatic fluid. So a fluid that just happens to be there in equilibrium with a carbonatite or a Brine-melt. Okay? And that's a bit different, because a year before in the elements paper, we actually did talk about a hydrothermal fluid. But this is science. You write something, and then the next year you discover it's not that accurate. Okay. Then we ran some more experiments. So I was an honor student, a student who wanted to do honors, Darby, and she said, I want to do experiments. Okay, well, let's run some more experiments. One of the big issues I had with my old experiments is that they didn't have any sulfate in them. And there's a big body of literature saying that sulfate is super important. You will not have anything without sulfate. So we did that. We recreated the experiments with sulfate to see what would happen. We also did some other changes, added an aerobie, which is for fun, added barium, because it seemed like it's important, because you always see them together. So we did one experiment. Well, we had a similar thing. Then we replaced atom by atom, mole by mole, carbonate with sulfate. And then we got this experiment. And there was another paper that said silica is important. So we did the same thing, just added a bit of silica, and we got this experiment. Okay, now I will not talk much about the silica stuff, but I will want to kind of zoom in into this part. Okay, so what do we have? Same sequence as before. We have calcite. This is a bit of dolomite. And then we have this mess here, which is, can you just go back to the legend? It's a whole range of sodium, potassium, sulfates, carbonates, stuff, chlorides, fluorides. This is the Brine-melt, okay? Now, we also have a hydrothermal fluid, and there's nothing else. Those crystals here, we're going into a bubble, and there's nothing in the bubble, okay? Also Bromokite, so the red pixels. So here's a big one, and you can find them. Here's one, here's another one. So those are Bromokites. Again, the mineralization is in the Brine-melt, not in the calcite, not adjacent to the dolomite. And you can map the thing on the microprobe and just look at where the elements are. So huge chunk of calcite carbonatite, not that interesting. And then we have the Brine-melt, has sodium, which will dissolve, sulfate, which will dissolve, and there are elements, and also chlorine and barium, which is why you always see them together. Now, what is really interesting is that those bright spots here are the Bromokites, so like a proper rare earth element mineral with tens of weight percents of lanthanum in this case. But you also see it in all kinds of different phases in the Brine-melt, which is, again, those all kinds of weird carbonates and sulfates and things that have just a tiny bit of rare earth elements, a weight percent. Now you can think that when you dissolve that, you're actually doing quite a lot of concentration of those elements into something that will be economic. Just something about the sulfate. One of the questions,
So you like the word brine melt.
yes,
What in your mind means brine? If you met me on the street and I'm interested in what you've been researching, I said, so define a brine.
an aqueous fluid with heaps of stuff dissolved in it.
So fluid, and why does it become a melt?
Because
Define melt.
this phase is distinct from a fluid. Now, you might say, yeah, okay,
That was a single homogeneous phase with all those colors in it.
yeah,
Yeah. So all of that stuff's come out on quench.
some on quench and some on cooling down. So this was cooled down to a 200. So at some point, just crystallize things. And the way it behaves, the way it transports elements is different from what we think of a brine. Because again, you remember that Miglitov and Willie Jones paper, they said, oh yeah, if you have chlorine and sulfate, you can dissolve stuff. If you have phosphate, you don't. Here is one phase that dissolves everything. Okay, and the other thing, this isn't actually that wet, because if it was wet, you'd see so much more holes in here, and you don't. So this is very low temperature eutectic salt with some water dissolved in it, which is not quite a brine, but it's a brine melt.
So if you made up that brine melt composition, bulk composition, and ran it by itself at the same pressure and temperature.
It would probably be liquid.
Yeah, and would it be saturated with dolomite?
I think so. I mean, this thing is touching dolomite, so I'd guess they are in equilibrium.
Yep.
Penny?
Trying to understand this as a fluid, do you think that the brine melt and the hydrothermal fluid are one thing at high temperature and pressure, and that you're looking at like the other solvents, and that the brine melt is the high density stuff, and the whole is the low density stuff? That hydrothermal fluid is brine melt.
Yes, but in the sense that silicate melt and bubbles in porphyry deposits were above the solvents and then they went down.
But it doesn't reflect the solubility of water.
Yeah.
I mean, if you've got more water than can be dissolved in the brine melt phase, then you have solids.
Yeah.
Yeah, it'd be interesting to do what Reed suggested. Right, and then the add water to see if you need that fluid.
Okay.
Create that. That makes.
Yeah, it does. Now, the thing is that this thing is a continuous evolution from the actual melt. Now, usually when we think of brines, we think of boiling, right? If you have a fluid that has an intermediate amount of ore elements and then it decompresses, it boils, then you have a high density phase, the brine that stays there, and then a low. This is not what is happening here, which is why I really don't like the terms that we know from silicate systems for this. It behaves differently, okay? Because in silicate systems, what you have, you reach 700 or 600 degrees and the melt is solid. It doesn't do anything. It stays there. Here, it just keeps on going, down temperature. Okay, we've seen this. Sulfate, yeah. So one of the questions that Darby tried to answer was, is sulfate important? And I think this gives a very clear no. In here you have some kind of melt inclusion in between calcite and salt is shortite. Shortite is a sodium calcium carbonate. And in between you have all kinds of sulfates and carbonates and halides. And here's a bourbonkite, and this bourbonkite is just sitting there in a pool of molten sulfate and it doesn't care about it. So if sulfate was important for the dissolution of earth elements, you would see some lanthanum here, and you don't, okay? And the other thing is that the carbonates, so the shortite, has earth elements in it, okay? So it's sodium calcium carbonate that has an amount, 0.5% or 8% or 2% orbit zone of earth elements. Shortite is a sodium something carbonate, will probably not survive 1 billion years of Earth's evolution and will dissolve. Okay, now this very experiment, we have it sitting now in a bucket of water just to see what will happen when we expose this. And one of the things that could happen, for example, how do you make barite? Because here's the barium is here and the sulfate is here. So the idea is that sometimes the anions can come from 10 microns away, which is again why having a balanced reaction doesn't make much sense because it's unconstrained. So is it coming from here? Is it coming from 10 centimeters away? You can pretty much make up anything you want. So why even bother? Yeah, why did I have that slide? Again, I'm not sure. But yeah, the point is that you have a rock in there. Okay, this is a rock. Okay, it's made of sodium carbonates and things which are soluble. But when it is forming in a magma chamber, again, whether they exist or not is a good question. When it's forming, this is a rock. It just sits there. Okay.
Don't you show your beautiful map with sulfur and chlorine?
That one.
Yeah, that same view, but yeah, sulfur
Yeah.
and chlorine. No, the other one you showed earlier.
No, that one.
Yes. So you could suggest that butterfly in the lower left there,
Mhm.
that it's rich in rare earths because it has so much sulfur and chlorine in it.
So
And then you can't fuss about what phase it's in now because you've already said that's irrelevant because the stuff.
indirectly, because what happens if we go back to this one, this experiment, no sulfate, and it does exactly the same thing. So you have here are some boracites. So other than the fact that some of the sodium sulfates are actually sodium carbonates in there, it looks almost identical. You have the calcite, you have the dolomite, and you have the brine-melt phase, and in there you have boracites. So it's essentially adding sulfate doesn't change this, right?
Well, that would be worth quantifying if the total TREOs in that polygon is the same as it is in the sulfur bearing and the chlorine bearing, then you have a better argument.
Well, it would be because you don't see any earth elements in the calcite.
Well, but we all know that.
Yeah, so, but you know,
Right?
I start with the same. Now it could have some differences, but then again, this is because it's changing the composition of the brine melt and therefore changing its solubility, not because you have H2O dominated fluids with sulfate in them that magically transport earth elements from one part of the deposit to another part of the deposit.
No, but it could be a crucial part of the brine melt.
Yeah, and look, I think you will always have some sulfate in brine melts. It's just right because this is what carbonatites are made of.
Right, but
Barite is one of the most.
The question is the sulfate bearing brine melt a better carrier of REE than a sulfate bearing brine melt?
Excellent question. Can probably be done experimentally in 2 weeks.
Well, what are you waiting for?
Me? Well, I'm looking at you one. Yeah, there you go.
Detail, you've got periclase in the key there. Where's the periclase in the experiments?
Oh, so this just in here, that was because magnesium carbonate doesn't like being at too high temperature, so it decomposes. It was an experimental oversight by me, but it doesn't change this. So, look, the thing is that all it did was just remove a bit of the magnesium, which is why the dolomite is thin and not as big as the other experiments. But I don't think it changes anything for the brine.
I mean, kind of one of the things that really puzzles me about carbonatites is how they actually get a crystallized dolomite.
You need low enough temperature,
Yeah,
which is why it's late in the sequence.
yeah, but even light, I mean, any of the phase diagrams, like the classic whole Peter Wiley type stuff, you never, very rarely get to old because it's really difficult to get rid of. It usually forms as a result of exsolution.
Yeah, so
Lower temperature.
I guess it's just a balance between the pressure and temperature. And to be fair, in my experiments, I rarely had experiments where I didn't have dolomite. So yeah, it's there. I made it.
It's a puzzle.
Yeah. Getting a bit late. I'll try to speed things up. Okay, so I was talking about the solubility of the things. On the right is one of my experiments immediately after I made it. And you can see it's all nice. Here's a bromactite. This is one of those weird amorphous sodium earth element things. Some carbonates in here. And then in 3 years of just sitting in a box in my office, away from rain, away from everything, it's decomposing, have holes everywhere. So this stuff is epoxy, which stays there. And like they're just disappearing. Where moisture, I don't know, bacteria, whatever, it goes somewhere, right? So those things are gone pretty quickly. Same thing. Here's a huge hole. This was a mineral and it's not there anymore, right? And it became this. So those things are not stable. Now, if you have some kind of sodium carbonate phase that has half a weight percent of earth elements, you pull out all the sodium into those thingies and you leave behind something that might look hydrothermal, like what we've seen in one of the first slides. Okay? And this is important because very often those internal core parts of carbonatites are vitiated. And you can also see that in the first Brine-melt paper where they have, there's a map and they have ore bodies. So that's where the mineralized carbonatites are. And then you have a breccia zone and it's always around them. Now they interpret this as explosive because, you know, it is a carbonatite, it is a magmatic system. Sometimes they blow up, okay? But there's an alternative idea that maybe those are the karsts. So here's an example of Cummins range, which is a very simple carbonatite. It has two kind of carbonatite bits, one here and there, and this one has an iron oxide, so a ferrocarbonatite altered one core that will have the mineralization, and they call it a collapse breccia. So it's a karst. Here are some pictures from samples I got from Cummins range. How would you define this rock? Like if you had it, is this a sandstone? This is sandstone. Now, almost everything you see here is apatite, and it keeps the crystal shape. Like if you look closely, you can still see some hexagons, and they're nice, and you have all of this, and there's nothing in between. In some cases, you have holes where you probably had the mineral, it even had a crust on it, but then the mineral itself disappeared. Here's another example of those apatites, and this one is a bit hexagonal, and if you look closely, some of them are, all of those are monazites. This is either magnetite or ilmenite. See, nice crystal shape. So here's a sandstone where we have all sorts of minerals that retain their crystal shape. So this wasn't transported in a stream or sediment somewhere. This could have been a plutonic rock made of sodium, soluble sodium, potassium, carbonate, sulfates, and stuff with apatite and monazite, but all of those things here, monazite, in between. It sits there, it rains on it for 1.5 billion years, and you dissolve all the stuff away and it just sinks down, leaving this behind. Here's an example of a mineral from there. Now, this is made of two rare thermal phases. One of them is kind of a basmasite, one of them is kind of a monazite, not quite. Very fine grained. I'm pretty sure that if we go in an atopore, we'll see all kinds of heaps of weird things happening there. Now, this could have been one of those weird minerals that have a certain amount of weight percent of earth elements, a sodium phosphate fluoride or something, and it dissolves and it leaves this stuff behind. So there was no fluid, external fluid that moved earth elements around and put them in there. This is just the remnant of weathering, of dissolution of a larger volume of plutonic sodium carbonate rock.
What's the black platy stuff in there?
In between, epoxy. It's like holes.
Did you
Okay?
make your in sections in water?
Hmm?
Did you make your in sections in water?
Never. Never. something I learned very early on in my PhD on carbonatites, that never let them touch any water, ever, because things will disappear. Okay, now, this is something new. So I spent the past hour or so telling you about that predictable structure where we have a calcite to dolomite to ankerite or siderite, and then there in the center you have your mineralized part. So this is an example from the Gascoigne, the Gifford Creek carbonatite complex, where it looks a bit different. So you have those carbonatite plugs in there, and then kind of dikes around. Now, when you look at the carbonatite plugs themselves, they're just carbonatites with like dolomite and stuff, but they don't have those ferrocarbonatite cores. When you look at the dikes around them, this is how they look. Those are just ironstones. Okay, so in this case, maybe what we had the crystallization, but then instead of just keeping the thing inside, contained, for some reason, structures, folds, whatever, the brine melt itself went out and made all of those things. Okay, so and those things were discovered like in the past 2 years or so. So a lot of unknowns, a lot of interesting things that can happen, and I think it shows the point very well of knowing, are those brines, are those melts, are those brine melts fluids, because each one of those will have different physical properties, different densities, different reaction with things. You were asking why I don't like the name brines, because brines will not form rock. Even though the brines are still mostly H2O, okay? Brine melts will make a rock before it's melt, okay? Almost done. So I'll just point out some things that I didn't talk about, okay? That are very important. So I didn't say anything about silica. And silica interaction with carbonatites and carbonatite melts is super important. You have all of those silicate rocks in the ring complexes, you have antiscarb, you have phennites, you have glimmerite, you have all kinds of things. I think you cannot understand a carbonatite system without understanding the effect of silica. But I only have so much time to speak now, so I will spare from this. Most of what I was talking about, I was focusing on rare earth elements. We don't know much about niobium, but I did play with that a bit in some of my experiments. So I think we have some leads, and maybe with your DP, we will learn some more things. But there are things to be said about niobium. I didn't talk about the fractionation between light and heavies. Okay, this is also something that my experiments and evidence from natures can tell you something about this in early processing carbonatites and also late. And point 4, I think, is very important. What are brine melts? So they are just salt melts, molten salts, where they formed by fractionating a carbonatite, and the most abundant anion is carbonate. Okay, but you can have salt melts of any kind of low temperature eutectic mixture of stuff, especially if you add a bit of pressure and water, you can melt everything at 400 or 300 degrees. And we know that brine melts can transport rare earth elements and barium and fluorine and iron and things that you would usually not see mobile together in traditional hydrothermal fluids. And carbonatites are only one way to make that. Well, what if we take an evaporite and melt it? Okay, so we can make all kinds of things. And there's a potential for a very wide range of new liquids or melts that exist in the crust that we have no idea about. Carbonatites are obvious because they crystallize into carbonates. Calcium carbonate, calcite, dolomite, those minerals are, you can find them. But if you had calcium chloride, you will never see it because it's soluble, right? And you can take calcium chloride powder on a humid day and it absorbs the water and then it dissolves in its own water. So those things, and it happens in minutes. So those things, I think there's a whole new kind of frontier in petrology, that there are things happening there that we have no idea. Okay, and I think this is one of the key things to solve the mysteries of IOCGs and IOAs. Okay, and I submitted an ARC application on that, and ARC, please fund me. Okay, so that's all. As a summary, because it was a long talk with many things. So some of the important points. So yes, we have hydrothermal fluids in carbonatite systems. They don't do much. They take some sodium, and that's about it. Okay, Brine-melts, a name that I adopted from the literature, where we just take a carbonatite and you continuously fractionate it. You lose the calcium to calcite and some dolomite. And then you have all of the other things, iron, rare element, barium, and things. When you look at fluid and melt inclusions, some of those brine melts, especially if they're wet, they can look like fluid inclusions. But then you need to look at the actual fluid inclusions and understand that it's not the same thing. And, you know, I think a very interesting idea is that, can you actually form plutonic rocks from there? If you have granites, can you have things, sodium carbonate rocks, like we know we have them as lavas or donolengai. Well, what would happen if this didn't erupt and just stay there in the crust? Okay, and again, don't be fooled by the hydrothermal appearance of minerals. Fluids in ore do not mean that this is the ore forming fluid. Okay, so that's all I had to say. Thank you very much, and happy to take any questions. Nav.
So Henri Fan has a paper on
Who?
Fan, Fan.
Oh
I
yeah.
can't pronounce his first name. Chudman, what's his first name?
Right.
Yeah, that. And he has pictures of briny, fluid vinyl, they're loaded with rare earths. So it's not fair to say we haven't seen rare earths in flinks in these deposits.
They're not flinks, they're minks. That's the thing.
They look flinky to me.
Exactly. Which is exactly this point. So how do you define the mink and a flink? So a mink.
I'll tell you, one solid at room temperature.
Okay, but again, the brine-melts, they will have some water. So this will be a bit liquid. No, because
The difficult discriminant to use, John.
Yeah.
I think.
You need water, actually.
No, but just, if you give me a mink, we'll look at it, and you heat it up, and it doesn't do anything until you get it to 500, and then all of a sudden, the bubble starts shrinking. You have a flink, and the bubble starts shrinking immediately.
Exactly, because those things, it's a continuous thing all the way down to very low temperature. And I think it's very important that we unlearn everything we know from those things in silicate system, where, okay, a mink is obvious and a flink is also obvious. It's hybrid, which is why I think we should give it new names, because it's not the same thing.
It's not so simple. That years ago, I was ridiculing Richard and all of his igneous petroleum friends for having only two words, a vein and a dye. Knowing full well in porphyries, there are things that are in between. They have too much in them to be a fluid, and there's no way they're an alkaline position. So I was ridiculing him for years for having such a shit way to call these rocks, and Richard had nothing to come back, but eventually these fell on. People started using the term in silicate systems, vein dike.
Wonderful name.
Right.
I love it. Yes. Yeah.
Another vague term that says it's somewhere in between, we don't know what the hell it is.
Yeah.
Which means it could be the same, and also I think pegmatites have the same stuff.
Pegmatites are a whole different story, and don't get me started about pegmatites. Yeah, look, again, it's you know, it could be semantics, but again, those things are important because you have fluids or brines or brine melts or melts or whatever that have different chemical compositions. They migrate differently to places in the system, because if we think that, oh, well, all of the elements are in a fluid and it goes out of the carbonatite, then we're exploring in the wrong place, right? So understanding what those things are and giving them names is very useful to finding them. Or if you find a deposit, find more in the deposit. Okay.
You're not supposed to talk for an hour either, you know?
Here's the door.
Like 45 minutes.
But in his defense, he didn't speak continuously.
So the rare earths are enriched brine melt just because they're incompatible in the evolving system, rather than brine melt having an intrinsic property that concentrates them.
What is the same thing? because yes, they're incompatible in calcite, they're incompatible, but they're also in apatite unless you have certain conditions. You know, when you're fractionating a silicate melt and you're taking out all the magnesium and enriching in sodium, is that because the silicate melt itself has something about sodium, or is it because it's incompatible? Well, it's the thermodynamics of the entire system, right? So it's we usually think of let me put it that way. When we think of all elements, we think of their solubility in a chemical system. Okay, like we want to know what the solubility of copper in silicate melt. So we run an experiment, C-mass composition, and we put some copper in. We don't consider the system as C-mass copper, right? And the earth elements are integral part of that system. So talking about that, like do they concentrate, like do silicate melts concentrate silica? It's not an easy question to answer.
But I think what it means, the opposite of what it is that, you know, you show with Darby's experiments that sulfur is not really useful in terms of transporting the rare earths, right?
Maybe. Experiment spending.
But you could have a brine melt with plenty of sulfur in it and plenty of rare earths in it.
Yeah.
So that's kind of the opposite.
Yeah, I mean, you were saying that the solubility of the rare earths in the fluid is low, and the fluid has potential complexing ligands of water, chlorine, sulfate and carbonate, not particularly good agents. In your brine melt, the potential complexing ligands are just the same as what you've got in the fluid.
Yeah, but
So their enrichment should not be due to their coordination, their stabilization by complexation. I'm asking, wanting to confirm if that's correct, that it's just because of the fractional crystallization, therefore very compatibility enriching.
yeah, but I think that thinking about this in terms of complexation isn't entirely correct, because complexation, again, you have complexation is something we mostly think about in hydrothermal fluids, in aqueous fluids. You have H2Os around, and then you have an atom and it bonds with this complex, and then you have an H2O something around it. But this is not what you have in biomass, because you don't think of let's say the solubility of copper and silicate melts as a complexation thing. Maybe you do, by the way, but it's not often thought that way.
So you're saying that
It's just part of the melt.
essentially a major component.
Yeah, it is a major component of the melt. Yeah, exactly. You should consider them as major components, and there were experiments by Wiley decades ago showing that the solubility of earth elements in carbonatites is essentially infinite, and until you saturate I don't know, a Parsnite or something. Penny.
It's back to your picture from that paper with the bone sample cell.
Okay. It'll take a second because the computer is a bit slow.
Oh, sorry.
I'll get there eventually. Maybe I can just do this and go.
Oh, it's got things in the chat.
Oh, stop the sharing by accident. We'll bring that back in a second. Well, it's this one. Yeah, and start sharing again. How do you stop the sharing? I made a mess. And it doesn't.
They went to sleep with mother.
Zoom, share. Good.
Oh, good.
Full screen. Good. Yeah. Yes.
So would these experiments show your brine melt somewhere? And if so, where is it?
Yeah.
It's so this thing here, like this is the brine. It's one phase. It's in there.
It's really weird when they show these pictures with nothing in it. That weird sulfate geology paper did the same thing. You can't tell if it's full on mineral or if it's just empty.
Or is it
that's-
just
I mean,
one
that-
fluid above the
I
salt?
mean, what the hell is that?
Yes, but the sulfate geology paper don't support my idea and those do. So I'm cherry picking this paper to support what I'm saying, right?
So, okay, so at 3.2 kilobars, you start crystallizing whatever that thing's in the like,
In here,
yeah.
this sodium carbonate, I'm guessing. Because it's NC here. I mean, I can check the paper again, but
Yeah.
I think Tim is saying, yeah, okay. I believe Tim is a good student.
So you got some things in the chat there.
That's all. Thank you, Michael.
So, following on from that, Michael, is there a certain pressure or something where the water starts to come out of the carbonatites?
So again, the range according to now with those experiments, it's a bit hard because you're long and isochloride. But the impression I was getting is that it's around a kilobar, but I guess it also depends on how much water is in there or how much excess CO2 in addition to the carbonates is in there.
So how much carbonate is that? Looking for your experiment, not that much, looking in your board experiments.
How much CO2?
Yeah.
What represent? 30 something?
30.
30 high 30s.
So do you have a feeling for how the graph of fraction of melt remaining versus temperature is on this? Do you crystallize your carbonates kind of continuously, or do you crystallize a lot of carbonates and then sort of flatten down and then you crystallize your salts right at the end, or what?
I don't know. So
You spoke too long, I have to leave, sorry.
by math. So to do that, you need many experiments to map out the phase diagram. And my approach is to do less experiments. But yeah, I mean, see, the problem is that once you go beyond simple systems of calcite and dolomite or CMAS, all of those, you have so many components that trying to map the phase diagram gets very hard. Like how many years of your life do you want to invest into doing that?
But when you've got lots of components, it's harder to get into the next solution. You've got to think about the phase.
It is. No, so like each type of experiment has its own benefits and problems. Yeah.
But if you want to ultimately understand how you create mineralized systems, it surely makes a difference if you know, the rate at which you concentrate the rare earths into the melt, you know, versus temperature or whatever.
Yes, important. I agree.
Go back to like this next paper.
It doesn't look like it's reversing from the diaphragm.
That one or the pictures?
Okay, I'll ask you later.
Okay. Yeah. And we can read the paper. It's a geology paper, so it's only like 4 or 5 pages.
Yeah.
Okay.
All right.
Okay, cool.
You think, Michael?
Now, enrich the people for you. Really? Oh, nice. Where is the body?